Alright, so today our goal is to utilize GSP in order to prove the sum formulas for both sine and cosine. So if we look at what we have here, we drew in this relationship, which is something that we should already know, that given the radius of a right triangle and a given angle, we know that the side opposite the angle must be r times the sine of the angle, and the side adjacent the angle must be the radius times the cosine of the angle. So we're going to utilize that relationship a little bit throughout this proof, so we wanted to put that over there just as a reminder. So if we look here, we drew a unit circle and we drew a right triangle whose hypotenuse is the radius. So based on the previous relationship that we mentioned earlier, the opposite side here from angle A would be the sine of A, and then the adjacent side would be the cosine of A. So what we'd like to show is the sum of A plus some other angle, show the relationship of that show what the actual relationship is. So what we're going to do is we're going to rotate this triangle by some angle which we're going to call B. So our goal triangle then will be this triangle A plus B is what we named it. And we're looking at this angle down here, this angle right here, which happens to be this side opposite, since we're looking at the sine of A plus B. So we're going to look at a few different triangles in this diagram, and the first one we're going to focus on is the one if we drop this perpendicular down right here, and if we pull that triangle up, we will see that the hypotenuse of this triangle, since it is the base of the original triangle, has to be the cosine of A. And then based on the relationship that we mentioned previously, that makes this side opposite the angle B, well, it's the sine of the angle, sine of B times the radius, which is the cosine of A. We're going to utilize this one right now for the proof of sine of A plus B. So we're going to go ahead and hide this triangle and pull that segment back up, just for future reference. So now we'd like to show a pair of lines that I just hid, but I meant to have them hidden earlier. We're going to draw on a couple more lines so we can look at a few other triangles in the diagram. So we're going to draw in this vertical line, which goes through this vertex of our original triangle, perpendicular to the base of the second triangle that we just drew. And then we're also going to draw this line, which is perpendicular to this vertical line and through this vertex of the original triangle. So the first triangle we're going to focus on is this one right down here, which if I put it into the diagram, we'll see, well, that includes angle B that we identified earlier, and then another angle which we're going to call C. So if we do a little bit of geometry, we can see that these other two triangles exhibit a relationship that's going to be useful for us. So if we go ahead and show those, we'll see that these two angles must be congruent because they are vertical angles, and then hence that makes this angle here must be angle B, since B and C are complementary and this forms a right triangle. We can use similar logic to get this teal triangle. The angle C has to be complementary to angle B, and then thus that makes this angle B, since this is a right triangle. So then we can utilize our right triangle relationship again. We know that the hypotenuse of this teal triangle is the sine of A, and hence we know that this vertical leg, which is adjacent to angle B, must be the radius, the sine of A, times the cosine of B. So that's going to be the other part that we kind of need to prove this angle sum formula. So now I'm going to hide out all these triangles again and focus just on that segment. And if we recognize the segment we identified before from that first triangle, the cosine of A times the sine of B, actually is congruent to this segment right here, which I will go ahead and show that one. So now if we pull back in our goal triangle again, we notice that, oh, we actually have the total length of the side that we're looking for, which is identically the sine of A plus B, which we now recognize has to be the sine of A times the cosine of B plus the cosine of A times the sine of B, which is the desired formula that we were looking for earlier. So now what we'd like to do is move on to the cosine sum formula, which is just the other side of this triangle. It's the base of this right triangle. So we'll go ahead and hide some of these other segments that we don't need. And I also want to hide this one here. So if we pull back up some of the relationships that we mentioned earlier, so this first triangle, we're going to want to put our focus on the base of this triangle, which is just the cosine of the angle B times its radius, which is the cosine of A. So we're going to go ahead and show, we're going to keep that segment in there. Oops, wrong one. And what we'd like to do is, if we know what this segment is, we can actually just subtract it from here, and that'll give us the base from our gold triangle, which was the cosine of A plus B. So if we pull, let's see, pull up these two triangles, we found earlier that this side, the base of this teal triangle, must actually be the sine of A times the sine of B, since it's opposite the angle B, whose hypotenuse is the sine of A. So then if we pull up the gold triangle here, we now see, I'm actually going to move this just a little bit out of the way. We now see that this whole bottom segment is the cosine of A times the cosine of B. This segment here is the sine of A times the sine of B. And we recognize that the cosine of A plus B actually has to be the difference between those two, which is identically the same, the formula that we were looking for, the result we were looking for, the cosine of A times the cosine of B minus the sine of A times the sine of B. Well, that is it for our proofs of the sum and angle formulas. I hope you enjoyed our little video. Thanks.